All right, so I suppose I should share my screen first so you don't just have a black screen. Blanked out there. No one's on, so I'm just recording this for myself. I'm assuming you guys are spending time with family, which of course good, you know. That's a good thing because of the holidays. So I'm going over graphing exponential functions. So I'm not going into everything that is in the section that talks about exponential functions because I'm just specifically going over the graphing portion of it. So I'm not going over solving, evaluating, or any of that, just graphing. So first, in order to graph something, we need to understand what it is. So the math definition of an exponential function. So let b be a constant real number such that b is greater than 0 and b is not equal to 1. So it's a positive number that's not 1. And then for any real number x, a function of the form f of x equals b of x, b to the x, sorry, is called an exponential function of base b. Now, some textbooks use a to the x, b to the x. It doesn't matter what variable is used as long as it's in the same form. Now, a lot of people get confused between polynomials and exponents because they both have exponents. A polynomial has x as the base, while an exponential function has x in the exponent. So that is the difference. They form different shapes, and they're very different functions. And so when you say something grows exponentially, it must be an exponential function. So if it's like an x squared, that is a polynomial, so that does not grow exponentially. That grows squared. Exponentials grow exponentially. X is in the exponent, so they're very different. And so as in math, the language is very important. Using the definitions is very important. You want to use the words precisely. So the way that I describe what the graphs look like is totally different than what the book does. This is how I think of it. So we have two different types of exponential functions, growth and decay. Growth is getting larger, decay is getting smaller. So an exponential growth function is specifically when I use a in this case. So as I said, some books use b. So if our function is f of x equals a to the x in this case, because I learned it as a. So if that value, the base under the exponent, is greater than 1, so like 2 to the x, 3 to the x, 10 to the x, those are exponential growth functions. And so they get steeper and steeper as x gets larger. And then as x gets smaller, they start getting flatter and flatter. There are three key ordered pairs that you can use to graph any exponential growth function, and they're actually very easy to graph, which is why I focus on these three. So the middle point that I have in my graph is 0, 1. Exponential functions always go through 0, 1, because 0 in your exponent gives you an answer of 1. So that's really easy to graph. So you know where it's going to hit. And then 1 point in either direction with a positive 1 or a negative 1, then either graphs the base, because any number to the exponent of 1 is just that number, or if it's negative 1, it's the reciprocal, using those rules of negative exponents. So that gives us three key ordered pairs that you can use to sketch any graph. And all you need to know is you don't even have to plug in any numbers, you just have to know what a is, essentially. So this is how I graph my exponential functions. It makes it so much easier. Now, some key things, the domain for exponential functions is all real numbers, so it goes from negative infinity to positive infinity. The range is 0 to infinity because it never gets below the x-axis. The only way it will get below x is if you have some transformations. We have a horizontal asymptote at y equals 0 because there's no way to actually get 0 as an output of an exponential. So there's a horizontal asymptote, but there's no vertical asymptote. Exponential growth is decreasing everywhere. It's just going up and up and up. So that's an increasing function. And it's continuous, which simply means that I can draw it without lifting my pen off the paper. So when we compare this to the decay is sort of a reflection of it. And so again, I'm using a here. F of x equals a to the x. And it decays if your value is between 0 and 1, like 1/2 to the x. That's where it's a decay. And I still have the 3 key points. It still goes through 0, 1, but it's a flip-flop. You can see, if I convert, it is a reflection across the y-axis, essentially. It flip-flops the y values, what they do for a -1 and a +1x. But the shape is roughly the same. It's just a mirror image. Our domain is the same. The range is the same. The horizontal asymptote is the same. The difference is that decay is decreasing. That's the only difference. And that's what makes the shape go down. But everything else basically stays the same. And so when I graph these, I use that table. I just determine what is my base A, or as our textbook uses, B. And then I plug it into the table, and then that gives me my graph. It's just that simple. So, of course, there are some transformations of these things that can change what your graph looks like. And so this is the general form when we have transformations. So order of transformations is x first, because alphabetical order. So that would be this x minus h. So just like any other transformation with the x, it shifts left or right. And just like any other transformation with the x, it does the opposite. So if it's x minus 2, it's going right 2. Then we have our transformations for y, and we always start order of operations, so multiplication comes before any addition. So that is a. So if a is less than 0, meaning that it's negative, and this is the form the book uses, so this is why now b is the base. I should have corrected my other thing to be B to be consistent, but I already have the image formed, so I didn't want to rename the image. But the number in front of our exponential part, a in this case, if it's less than 0, it's a reflection. Just like that negative in front of something reflects across the x-axis in any other transformation. And it also is the vertical stretch, or the shrink. So just like all other transformations, that number in front stretches or shrinks it. And then the last one is k, where we move it up or down. And so that is our shift up and down, just like everything else. Now, when we talked about quadratic functions, h and k were sort of like the vertex. You can think of h and k as sort of where this middle location is, the 0, 1, as your h and your k. So those will sort of move based off of, so your kind of center of the 3 points you can think of as your vertex. It's not technically a vertex, but it's similar when you think about it. So those are transformations. And so now we're just going to go straight to graphing, because this is what you're here for. You're here to learn how to graph these things. So we have 2 to the x plus 1. So transformations here. That 2 was not a transformation. That is our base. So our function, I'll use the book terminology, b to the x. So in this case, b is equal to 2. So our base is 2. So that is not a stretch or shrink. That's part of the function. So we have a plus 1 here. That is our vertical shift up. So we are shifting up 1. And when we shift up 1 unit, what that does is it moves the vertical or the horizontal asymptote up 1 unit. So now that is now at y equals 1, because that is also involving vertical stuff. So horizontal asymptote shifts up along with it because it's a y equals equation. And our range shifts. So the range is normally 0 to infinity as written on these graphs. Now here, because our base is 2, we got a growth. So range is 0 to infinity, but now that we shifted up, it's now 1 to infinity. So the transformation changes our range so that it's 1 to infinity. So that shift does several things. So it said identify the transformation. We didn't have to write down the horizontal asymptote and range at the same time, but because it also says identify the domain and range and give the equation for an asymptote, I wanted to link those together so that you can see what shifting up and down does to those. They work in concert. Shifting up or down affects horizontal asymptotes and ranges. It does not affect domain at all, or vertical asymptotes. Those are the X things that change those. So graph the function. So I've already identified my horizontal asymptote, so I'm going to just draw that in at 1 very lightly. Now it says graph the function. So like I said, normally, let me go back to the right, I would just use this table with x, -1, 0, 1, y is 1 over a, 1, and a. Now I use a here in this case, but it's the same as b. I'm going to use this table, and then we're going to use the shifts so you can see what happened to it. So I'm going to basically copy this table down, and then we'll use it for our transformation. So I'm going to do this in white. So normal f of x equals b to the x. We have -1, 0, and 1. It's 1 over b, 1, and b as our y values there. So if we shifted that up 1, then that means it's going to be basically all of these y values are up by 1. So it'd be 1 over b plus 1, 1 plus 1, which is now 2, and then b plus 1. So that f of x that we have of 2 to the x plus 1, everything got shifted up by 1. So instead of 1 over b, that's 1/2 because b is 2. So 1/2 plus 1, that's basically 1.5. Then we're going to be at 2 instead of 1 because we went up 1. And then b is 2. So that's going to give us 3. And so that gives me my 3 y values that I can graph. My x values are unchanged because we didn't shift left or right. We just literally went up and down. So at -1, I'm now going to be at 1.5, so I'm going to estimate that. Then 0 is at 2, and at 1, I'm at 3. And then I just connect, and then because we have an asymptote, I can make it go close to the asymptote. So I just plot those 3 lines, connect them, and that's my graph. Now the thing about domain here is that it's all real numbers. It doesn't matter what your graph looks like. It's always going to be all real numbers. Shifting left or right, up and down doesn't change that for exponentials. So going in order here, I identified my transformation. It was a shift up of 1 unit. I now have my graph, domain and range. Domain is all real numbers. Range is from 1 to infinity. And then the equation for the asymptote is y equals 1. Okay. Here we've got f of x equals 3 to the x minus 2. So let's identify b. The base in this case is 3. So everything is going to be in terms of 1/3 and 3 when we graph. And 3, it's between, or it's greater than 1, so this is going to be growth. So transformations here. This is a left or right shift shift left or right because it's x minus 2. So the minus does the opposite, so it adds 2. So we're shifting right by 2 units. We don't have any other transformations going on there. So now let's graph the function. So I'm going to go back to my base with -1, 0, and 1, and then this is 1 over b, 1, and b. So just to be clear where this table comes from, my base 3 is greater than 1. So I'm going back. This is a growth function, so I'm just literally copying my table here and using b instead of a because that's what the book is using, but it really doesn't matter. So I'm just copying from this table. So transformations here. Our y has no transformation, so I can just plug in my number for b. So that gives me 1/3 and 3 as the y values there. Now, we did have a horizontal shift, and we went right 2 units, which means we're adding 2. So you're adding 2 to each of the x values. So my new x values, 2 plus -1, that is 1. 2 plus 0 is 0. No, not 0. 2 plus 0 is 2. 2 plus 1 is 3. So this gives me new ordered pairs. 1, 1/3, 2, 1, 3, and 3. Shifting left or right does not affect the horizontal asymptote, so that's still at 0. So I'm going to just draw that in. And now I'm going to graph. 1, I'm going to estimate where 1/3 is. 2, 1, and then 3, 3. And then I connect it, and I go towards my horizontal asymptote. And there we go, that's our graph. So now I've graphed the function, identify domain and range. So our domain is always real numbers, doesn't change. So it's always -infinity to +infinity. And the range here, we didn't move anything. We didn't go up or down, so it's the same as the range of a normal one with a base, which is 0 to infinity. And then our equation for the asymptote is at y equals 0, because there was no vertical change to move that asymptote. Okay, here, now we have f of x equals 4 to the -x. So we haven't really talked about what happens if there's a negative in your exponent with the negative with the x. Technically, that would be a reflection over the y-axis, but it's a lot easier if we use our rules about negative exponents, where you can make it a positive exponent by taking the reciprocal. So this is really 1/4 to the x. And so when you look at it that way, our base is 1/4, and now this is decay. So this is going to be getting smaller versus larger. So we're going to be using our decay table. So transformation here, the transformation is technically a reflection across the y-axis. And we don't talk about that kind of reflection often because we don't normally do that reflection often. It's the only reflection that we really see a lot, and that's in exponentials. So going back here, you can see that here was the growth. When you switch to decay, it's flip-flopping across y. It's a mirror image across y. So that's a reflection across the y-axis. So we have a decay, so I'm going to be using this table here with -1, 0, and 1 for my graphing. and then these y values. So that's what I'm going to be using here to graph this one. So I'm going to put it in white. So we still have -1, 0, and 1. But now our base is b. We're still at 0, 1, and then it's 1 over b. So that is the form of the table for when you have a decay function, essentially. So our only change here, we have b of 1/4, so I'm just going to plug that into my table. So this is, wait a minute. Hold on. I'm like looking at this. Wait, nope, that should be, wait. Let me double check my table because I think I did some flip-flops. Yeah. Okay. This table, I forgot that. See, we switched textbooks, and the textbook did this differently. So, oops. Because the textbook wrote it as f of x. Oh, I don't want green. F of x equals a to the negative x, and then that's what this table goes with, is f of x to the negative x. So this would still be, if I'm going to be consistent here, that's still 1 over a, and this is still a right here. It's just a is between 0 and 1. So I was trying to reuse some notes and kind of didn't change everything. So what would be best here? Let's trying to see. I will just make a new slide here and put it in when I do the I'll just re-record this part. Because nobody's on anyway. Doesn't really matter. And I will do some editing. So going back here. Okay, so we're going to use the same 1 over b and b. So 1 over b, which is 1/4, 1 over 1/4 is 4, and then b is 1/4. So that is going to give us our y values here to graph. Our asymptote is still at y equals 0 because we're not shifting up or down. And so -1 is at 4, 0 at 1, 1 is at 1/4. Now notice that the bigger b gets, the steeper it gets. So it's sort of like its own little stretch. Because it just gets kind of narrower and narrower and narrower. So you can think of that value as a stretch itself. So you can see it reflected across the y-axis compared to other ones here. So I've graphed the function, domain, and range. So domain is always all real numbers. And the range here has not been changed by shifts, so it's still 0 to infinity. And then our asymptote's at y equals 0. That has unchanged. Okay, here we've got another one. This is 1/3, so our base here is 1/3, so this is decay. And that negative in front, that is reflecting across the x-axis. So our transformation reflects the reflection across the x-axis. Now what that does is It doesn't affect the asymptote because our asymptote is still at y equals 0. A reflection multiplying it by negative doesn't change anything. Negative 0 is still negative 0. But it does change the range. So our range, which was 0 to infinity, is now going to be negative infinity to 0 because it's making it upside down. So that reflection didn't affect the asymptote, but did affect the range. So that's going to change that graph. So graphing here. So we have x and y, negative 1, 0, and 1, and we always have 1 over b, 1, and b. So I just need to plug in my values for b. So b is 1/3. 1 over 1/3 is 3, so that becomes 3. And then I can replace b with 1/3. So now I have 3 points to graph. Negative 1, 3, 0, 1, and 1, and 1/3. But I forgot my reflection across the x-axis, which what that does is it changes all of the x values. It changes their sign from positive to negative. So that really is 1, 0, and negative 1 there. Because the reflection across x is you're multiplying, whoops, not the x, sorry, that's reflection across the y. A reflection across the x-axis, I have that negative. I need to now reflect or multiply those y values by negative 1. So that becomes a negative 3, a negative 1, and a negative 1/3. So now I'm going to graph those. Negative 1, negative 3, 0, negative 1, and 1, negative 1/3. And then I'm going to connect those and approach my asymptote. And so that's my graph. So it is reflected across the x-axis. So now it's basically upside down. So identify the domain and range. I already have the range here. Domain is unchanged. It's always all real numbers. So negative infinity to positive infinity. And then we talked about the equation for the asymptote. That's going to be unchanged. That's y equals 0. So one special type of exponential function uses E, which is Euler's number. I'm not going to graph these because it's really difficult to graph things which has a decimal that never ends, just like pi. So graphing anything with Euler's number, I would recommend using a graphing calculator rather than doing it by hand because you're going to have to do some rounding here. But just some information about Euler's number. So this was discovered by Jacob Bernoulli. And he discovered it when he was studying compound interest because it does tend to pop up, especially with something called continuous interest. But it's actually named after Euler. It's not pronounced Euler, it's pronounced Euler. He was the one that gave it the symbol E in 1727, and so he gave it a symbol, so he ended up naming it. And it's like pi, it's irrational, it can't be written as a fraction, it goes on forever. I personally know more digits of pi than E. I usually only remember that E is 2.71, but it would round to 2.72 if I had rounded that correctly. And it's commonly used for exponential functions. It's called the natural base. And you'll see E more often than you'll see any other type of exponential, especially if you're going into engineering, because it shows up all the time. But again, I'm not going to graph these because it's just difficult to graph by hand. But if you use Desmos to graph it, you just type in the letter E, and Desmos will know what you're talking about. So that's graphing exponential functions. And so you can use a graphing calculator, but usually they're not too hard to graph by hand. And I should probably bring up Alex to kind of show you some graphing. So let me do that just to show you kind of how that graphs. So give me a moment while I bring that up. It takes a bit to load. Okay, so I'm just going to go to the assignments. And so week 7 and 8. So we don't actually do any graphing of this stuff until week 8, but because it's in the reading, I figured that I would cover it. So I'm going to just open up this week 8 homework so you get an idea. Okay, so here's transformations, domain and range, asymptote here. Use transformations of the graph of y equals 2 to the x to graph the given function. So we have 2 to the x plus 2. So this plus 2 is shifting us 2 units up. So upward. Okay. So the parent function y equals 2 to the x is an increasing exponential function because 2 is greater than 1. So we can plot a few points on the graph of 2 to the x and use these points for a horizontal asymptote to form the outline of the transferred graph. Now they're using different values than I would. They're using -2 instead of like -1, 0, and 1. They're actually using, I used only 3 points. They're using 6 points here, -2, -1, 0, 1, and 2. So just keep that in mind. They're doing a little bit more than I would. But 0, 1 corresponds to 0 on our transformed, because we're not transforming the x, but we're shifting the y up 2. So 1 plus 2 is now 3. So this is basically walking you through transformations. So we have normally a point 1, 2, but now our y is up by 2, so that's going to be 1, 4. Then normally you would have the point 2, 4, but we're shifting up 2, so that's now 2, 6. So this is sort of doing what I was doing. It's just putting it in a different form. I think putting it in a table might be a little bit easier to read, but we're just shifting, we're taking original points and then shifting them up by 2. Okay, so now here's how we graph these. So this is, you got to pick the right shape. So we've got a growth function. That's going to be right here. So notice you have to do your horizontal asymptote first. So we shifted up 2. It's normally at 0, so now it's up here at y equals 2. Now when you want to place your points. So I like to place the 0, point. So that's 0, 3, according to what I entered in. So I'm going to hit that. And then we need to place a second point. So let's do the 1, 4. So 1, 4. And it will finish the graph for you. So here, now that's our finished graph. So I graphed by hand and used 3 points. It's a little harder. I would pick whole number points here, but it gets you the right shape. Okay, so domain and range. So the domain, I said, was all real numbers. So I'm going to make sure I put in my parentheses and then my negative infinity, my positive infinity, range. Now our range normally is from 0 to infinity, but because we shifted up, it's now from 2 to infinity. So I'm going to put that in. And then our asymptote, now it's shifted up from 0 to 2, so it's now at y equals 2. So y equals 2. Nope, 2. And that's it. So that's how you graph them here in Alex. So this walks you through basically the same process that I was walking you through, doing it by hand, just with a few more points. This is just evaluating, doing some other things with exponential functions, logarithms, things like that. But that's, let's check what problem 5 is. Graphing a logarithm. So that's sort of graph, very similar. You have to pick the right graph and you do your asymptote, all that kind of stuff. So that's it. That is how you graph exponential functions. And hopefully you found this helpful.